mini course on Topos approach. First of all, thanks for your interest, for being here. I will send around the slides via the quantum mailing list, so if you want to take notes, that's fine, but you don't have to in this sense. Today I will be quite non-technical, as already mentioned. I'll give you some of the background in physics, which helps you to understand why we are doing what we are doing in the Topos approach, and let's say from next week on I will start to hit you with lots of definitions and theorems and stuff, but it's better to know why we are doing that. So this should be comparatively easy, but we'll get in place some things about classical physics that we will refer to later on a lot, so this is still useful, I hope. Okay, organizational stuff. So, okay, today is Friday, of course, but we will usually meet on Thursdays, and I thought 13:30 to 15 o'clock is okay. If there's interest, we'll carry this on beyond this, but let's say I'm planning for these 9 sessions. First of all, we have a room, it's not this one, it's 147, for the next 2 weeks definitely. They tell me they can't fix this before all the classes are fixed, but I strongly suppose we'll stay in 147 months beyond this, so I'll let you know. So anyway, next week, if you're interested, we meet on Thursday in 147. This will be kind of a lecture course, but I really encourage you to interrupt me and to ask questions all the time if you like. I may refer some of the questions to, well, the second part of each lecture. I will not be strict about this, but roughly I'm planning to have, let's say, a core lecture. This is the first hour, and then a part where I move maybe some technical proofs, and there should also be time for questions and discussion and these things. And the aim, of course, to provide the necessary mathematical and physical background plus some actual definitions, results of the Topos approach, and hopefully in an accessible way. So it's really, my aim is mostly to avoid this, that people say, well, they sometimes say after hearing about this, yeah, it's very interesting, but I don't understand the technical stuff. So it's actually about giving you enough background and information to really understand what's going on. So let's first talk about physics. And I just had to put this quote by finding there. And okay, so the Topos approach is a shorter name for some work in mathematical physics. And in order to see what it's all about, we need some idea of the situation in physics, and of course also what the open problems are. Very generally speaking, in the last 10 years, because you can say actually started in 1900 and got really new ideas pointing in the direction of quantum theory. Started in 1900, Max Planck. And since then, physics has widened its scope enormously and on several scales. And on the one hand, the range of phenomena described. I mean, 1900, nobody knew how atoms looked like. Nobody knew that there were other galaxies. And all these things are nowadays described very well by physical theories. So this also points to different length scales to which we have extended our physical understanding. And of course also the mathematical sophistication and predictive power has grown a lot. And it's quite funny to know that in the 19th century, so shortly before this, there was a common belief that physics is more or less complete. And people were actually discouraged from starting to do physics because the belief was that you have to fill in a few more details and that would be it. So how wrong they were. So what was in place in 1900? There was what we call classical physics, or at least most of it. We'll see this. And so I'll say a few things about classical physics. First of all, what belongs to classical physics? It's the following theories. It's first of all mechanics, and this is just a theory which describes the behavior, and this mostly means the movement of material bodies under the influence of forces, for example, the gravitational force. And the main subfields are, of course, point particle mechanics. Well, Newton, this is, I think, the only work I'm actually quoting here from historical terms of Principia. This is really where modern physics started. This was 1668, and Lagrange and Hamilton reformulated and refined this mathematically. And later on, when I talk about classical mechanics, I mostly mean point particle mechanics in the form that Hamilton developed. Of course, there's also mechanics of gases and fluids. This is called continuum mechanics, and well, the most important historical names are Navier and Stokes. And some of you may know that, well, there is famous Stokes equations, which are differential equations, which are awfully hard to solve, and there are still open problems related to those differential equations, and you can win $1 million. It's one of the millennium problems, if you can show that the Navier-Stokes equations always have solutions and unique solutions. So there's money to earn on this. Thermodynamics, Clausius, Helmholtz and Gibbs, among others, show up here. This is the theory of heat and the conversion of energy. And this was later explained in terms of an underlying microscopic theory, which is statistical mechanics. And this Maxwell and Boltzmann. Of course, I'm always picking a few names, and the history is always much more complicated and there are more people involved. And so this is roughly late 18th to late 19th century. After 1900, there came special relativity, Einstein, 1905, and special relativity can be seen as a reformulation of classical mechanics. First of all, without forces, and this gives a lot of new insight about geometry of space and time. And the step is actually quite massive. I mean, people had been doing mechanics for 250 years, and then Einstein comes along and says, well, you thought about space and time in the wrong way. Here's a better way to do this. So it's a massive step. An even bigger step was general relativity, which actually allowed us to include forces into the description, especially gravitational force. And this is a very, very beautiful theory which describes gravitation in terms of geometry. And there is an interaction between matter, which determines what the geometry of space-time is, and, well, the geometry acts back on the matter in the form that tells the matter how to move. Okay, so this is mechanics, and there's of course also electrodynamics, which is mostly, well, it's more informed due to Maxwell. There's lots of other names also, and this describes electrical and magnetic phenomena, including electromagnetic waves, light and other phenomena. And the biggest step that Maxwell actually took was adding a term to equations that were actually there, but this term resulted in these equations having wave-like solutions in the form of electromagnetic waves, which were not known at the time when he wrote this down. So his theory predicted electromagnetic waves, and they were only observed in 1888 by Heinrich Hertz. Okay, so the theories that we have mentioned under mechanics, except for general relativity, are all theories about systems with finitely many degrees of freedom. So this degree of freedom is a technical notion, but roughly it just means the number of parameters that you need to describe your system. So if you look at point particles, which we'll do in a moment, you need finitely many parameters. And well, I was maybe not very precise here when I think about gases and fluids, then it depends on how we describe them. Of course, you may need infinitely many parameters. Of a different kind of theory are electrodynamics and general relativity, which are usually write GR just. These are field theories. And this means, well, if you have a field, you need to specify this at each point of space-time. So you need infinitely many things to be specified, so there are infinitely many degrees of freedom. And I would also like to ask you that when I say physical system, this does not necessarily just mean a material body, it can be a field, it can actually be, I can cut up an existing system in different ways. It can take, for example, even just a few modes of a field and call this my system. So it's a pretty general notion. Now, what is it that is described by the degrees of freedom? Let's take as an example something very simple from classical mechanics, a point particle moving in space. So what can you know about the point particle? Well, first of all, you have to say, I know this at some fixed point in time. And if at this point in time I know the particle's position and momentum, which is nothing but mass times velocity, I've completely determined the state of this particle. There's nothing else I could know. There's no inner structure. This is why I'm calling this a point particle. So this completely fixes how this system is. And now the equations of classical mechanics are such that if you know the state at some time t0, and you know the forces acting upon the particle, then you can calculate the state at any later or earlier time. So these differential equations have solutions, at least locally, so you may not be able to do this for all times. There may be global obstacles to that, but at least locally you can calculate how the particle moves. And mathematically you have second-order differential equations relating the position, the momentum, and the acceleration. Now, if you look at the values of position and momentum, they each have three components. There's x, y, and z component of position and likewise for momentum. And you can see them as coordinates in a six-dimensional space, and this is nothing but the state space of the system. It's just, this is very simple actually, because every point in this space is one possible state of this particle, and in this simple situation we just have R6 as our state space for a single particle. And more generally, there may be geometric conditions on how a system can move. Say I restrict movement on a sphere, for example. Then globally, your state space is not just an Rn, but locally it still looks like an Rn. It's just like if you look up some map in an atlas, it's a 2D representation of a space which globally is not 2D. And what I'm aiming at is a very intuitive idea of what a manifold is. So a space which locally looks like some Rn and can be covered by such patches which look like Rn. It's called a manifold. More specifically, we have more structure here. We have a real manifold because these are real coordinates first of all, and smooth means we have differentiable structure there. And I will not explain this, but basically it means I can define functions on the manifold. I can form derivatives and all these things, and actually every function can be differentiated arbitrarily often. And an important structure which I may say a bit more about later on is the symplectic structure, but I don't want to go there. Anyway, it is true that in mechanics the state spaces of systems are symplectic manifolds. If you go to field theory, you obviously need infinite dimensional manifolds. And this is not an easy subject, but you can handle this. Actually, even in Lagrange mechanics and talk about variational principles of paths, you actually have to go to infinite dimensional manifolds, which usually is not spelled out. Classical mechanics, but also electrodynamics, are very geometric theories that use a lot of differential geometry. That's the geometry of smooth manifolds. Okay, and now this is my favorite picture. I'll show this every time we proceed. Again, later on, this is a very rough representation of a state space, so we forget lots of structure, we don't display any details here. This blob is the state space of the system. It's all this. So it's a classical system, and I've already said, okay, the degrees of freedom, the physical quantities, and one thing I want to So of course they're closely related. Let's say our physical quantity is position. It's not exactly the same as a degree of freedom because position comes with 3 degrees of freedom in x, y, and z direction. Of course they're closely related. So let's say A is just a symbol for physical quantity like position or momentum. Physical quantity is the same as observable. Most people say observable. I say physical quantity. Such physical quantity is represented by a real value function, Fa, which goes from the state space to the real numbers. And this is actually very simple because such a function does just the following. It assigns to each state S in our state space a value. Just evaluate the function at this point and you get the real number. This is nothing but the value of the physical quantity A in the state S. And this is completely unproblematic. This is just a formalization of something very intuitive. The physical quantities have values and the state is the agent that assigns the values. I'm not quite sure why I write B here, but any physical quantity has a definite sharp value in any given state S, simply given by this evaluation. Okay. We generally assume that the physical quantities form some structure, they form an algebra, and this can be seen on the level of the representing functions by just saying, okay, I have an algebra structure in the following way. These algebras, first of all, are real numbers, and addition and multiplication are defined in the image, which means you just add and multiply real numbers here. And since addition and multiplication, well, in particular multiplication is commutative, we get an abelian algebra of physical quantities in classical physics. Depending on the application, you may want to consider smooth functions or continuous functions or just measurable functions. So of course, well, this is the smooth are contained in continuous and those are contained in measurable ones. We usually will just assume measurability, so we have the functions in the state space. Okay. But this already is really an important piece of formalization that we should keep in mind. This is very much how classical physics works. You have state space, you have physical quantities described as functions with real values in this space. And these spaces actually have a lot more structure, which we forget for now when there's symplectic manifolds. Well, we know classical physics is wrong. I mean, that's not the full story. So what's actually going wrong? Why did people realize around 1900 they had to do more? There were some phenomena that still needed to be explained, and I'll just name 3 of them. One was black body radiation. A black body is an idealized material body, which is black in the sense that it first of all absorbs all incoming radiation, and then of course it must get into thermal equilibrium with its surroundings, so it will give off radiation again, and you can at least approximately do experiments. Basically you take a box and poke a hole in it. This is very close to being a black body, and you see the spectrum of the radiation coming out, and it's a very particular curve, and you could explain it using classical physics. And then Planck said, okay, we can understand this if we assume that, well, as logically said at this point, if the energy can only be absorbed and be given off in small packets, and this is where the word quantum comes from originally. Other things, there was spectacularly good data on atomic spectra around 1900, so it was really an art form. The experimentalists were very, very good at producing atomic spectra. And there was the photoelectric effect. And all 3 of these phenomena have to do with the interaction between light, radiation, and matter. And now let's look at these atomic spectra for a moment. So, of course, people were very interested in how matter actually looks on small scales. And from 1911 on, other Ford's experiments, it was clear that atoms, so people had the idea of atoms much earlier than they actually had good models for this. So, but this was pretty clear. People also knew about electrons at this time, but they did not know until 1911 that You should think of an atom as being kind of similar to solar systems. You have a small nucleus and you have electrons pretty far away, and most of it is empty space. Now this is all fine, but there are massive problems if you look at this as a classical system. First of all, classically there's no reason why you should see discrete spectral lines as you actually do in experiments, because such an electron could move, if it was a classical particle, on any closed trajectory around the nucleus, and it could, in classical view, absorb any amount of energy and give off any amount of energy. So you wouldn't expect to see lines, you would expect to see some kind of continuous spectrum. But even worse, an electron is a charged particle, and the motion around the center is an accelerated motion. This doesn't mean the particle is getting faster, but it's constantly being diverted from the linear motion. So this is why this is an accelerated motion. And electrodynamics just tells you that accelerated charged particles give off energy in the form of radiation. So if this would apply, the electron would very quickly give off its energy and just fall onto the nucleus. And obviously this was not happening. So you have big problems here. And there were ad hoc models, Bohr's model of the atom in 1915, and there was a lot of intermediate steps, but finally people arrived at quantum theory. So of course I'm skipping all the details here. And you can find this in books and give you some nice references later. You can find something about this if you like. And so in the mid to late 1920s, quantum theory finally took its form as a new theory describing the physics of atoms. And this was what it was aimed at. So the early versions of quantum theory already succeeded in describing spectral lines of simple atoms. So think about hydrogen. So if your atom gets more complicated, which just means the nucleus is heavier, then it becomes harder to do this. But at least for hydrogen, this could be explained very well by the new theory. And it became clear that quantum theory can be applied to many more phenomena than just atoms. So there was something deep going on here. And final mathematical form that we're actually still using today was found by John von Neumann between 1928 and 1932. We had this famous books on foundation of quantum theory, which is, as somebody said, one of the most cited and least read books in the history of physics. But anyway, John von Neumann is a name you should keep in mind. So he was really enormously important in the development of quantum physics, but also many other parts of mathematics, and he's a very interesting mathematician. So now I'm in a situation where I know that some people know very well about quantum theory, other people know very little. So I will actually in the next lecture mostly, and then also beyond that, introduce some basic concepts of quantum theory. So at this point I'll just give you a table comparing things, and if you've never heard about quantum theory, many things will seem quite mysterious, but we'll talk about them. But I want to make this comparison between classical physics and quantum physics, and actually I should be a bit more specific between classical Newtonian point particle mechanics and non-relativistic quantum theory, and we'll see at least some of them, how different they are, and these things will, I hesitate to say all be explained. I'll talk about most of them, because we'll eventually reformulate things on this side. So here I have the abstract notions, and here I have how these things look in classical physics, and here I have how they look in quantum physics, obviously. So, as I said, the state space in classical physics is given by a symplectic manifold, while in quantum theory it's given by Hilbert space. I actually could have put a question mark here, which is due to the following. The way I introduced states is saying, okay, this tells you how the system is. You need to know everything that there is to know, and that's intuitively how you would use the word state anyway. This applies very well in classical physics, but it does not apply very well in quantum theory. So it's actually quite confusing that the word state is applied to a certain thing in quantum theory. It has a very different role from state in classical physics. But I can't get away from the usual usage of this, so I'll go with it, but I'll say a lot more about this, why quantum states are so different from classical states, and this actually has a lot to do with these conceptual problems of quantum theory that we'll come to. Okay, a pure state, what I said is what a point in the state space is a pure state. There is this notion of pure, which also will be explained, is not the most general kind of state. Let's stay with this for a moment. So this is a point in state space, classically, and it's an element of the dual space on the quantum side. A general state in classical physics is actually a probability measure on the state space. For example, if you have some lack of knowledge about your system, you may not be able to specify all these parameters uniquely, but you still have some idea about a probability distribution. Or you treat a system which has awfully many degrees of freedom as you do with statistical mechanics, then you're not actually interested in every position in x direction of every of your 10 to the 23 atoms. You want to know about certain macroscopic observables which still are stable under averaging, and so this means it's usually enough to know a probability measure. Corresponding notion on the quantum side is what a general linear functional. And we will have to introduce this. These are the bounded operators on the Hilbert space, and this should be of norm 1. So this is very close to being a measure, because a measure is also, well, an integral actually is a positive linear function of norm 1. Time evolution in classical physics is nonlinear, where you have these differential equations. These are nonlinear equations, and quantum side actually it's a linear equation. This is somewhat surprising. That's how it is. Physical quantities are described classically as functions on the state space, and in quantum theory they're described as Selvig-John operators. And I want to point out that these functions go to real numbers, while the operators map Hilbert space that we will introduce technically later on to itself. So there's actually a big difference here. The value of a physical quantity is just given by this evaluation. You take the function and well, you evaluate it at the state and you get a real number, that's fine. In quantum theory, again, there could be a question mark, because in general, in a given state, a physical quantity does not have a definite value. You can calculate something, it's called the expectation value. But we'll have to say more about this. It is true in quantum theory that in general you prepare your system in the same state, you perform a measurement of the physical quantity represented by A, and you can get different results. And you actually have to do statistics, and you get some kind of probability distributions about the possible measurement outcomes, and then you can take the expectation value. This is what you can calculate in this way. But it's also conceptually very different from the value of physical quantity in classical physics, because this is just the value that the physical quantity has. There's nothing mysterious going on here. While here it's much less clear. The algebra of physical quantities is abelian. Abelian means commutative, so I'll usually say abelian. For classical systems and non-abelian for quantum systems. Actually, more important physically than this structure is a Lie algebra structure on the physical quantities. So this is a very interesting topic, but probably I won't have much time to say something about this. On the classical side you have the Poisson bracket. This introduces an element of non-commutativity into classical physics. So it's by no means true that classical physics is always just commutative, and that's why things are simple. That's not true. Physically relevant structure, much more than the actual algebra of physical quantities, is the Lie algebra structure on the physical quantities, and this is non-commutative. In both cases, classical is a Poisson bracket, and quantum side is a commutator. And unfortunately, there's no easy translation between those two. There's strong theorems which tell you you can't have the algebra homomorphisms from a classical to a quantum situation in general. Composition of systems works classically via the Cartesian product of the state spaces and via the tensor product of the Hilbert spaces on the quantum side. This also has a lot to do with more states in the tensor product than you would have in the Cartesian product. We'll talk about propositions quite a lot, so I'll introduce this symbolic notation, which means a physical quantity A has a value in a set delta of real numbers. Arguably, physics is very much about this stuff. You want to talk about these things. I give you a system, and you want to know what are the values of my physical quantities. Of course, you need a given state to say anything about this, but at a very basic level, physics is about what can we say about propositions of this form and how they change in time when the state changes in time. We'll see that in classical physics this is just represented by a subset of the state space, and quantum physics is represented by a projection operator P. This actually comes out of the so-called spectral theorem, which we'll prove next time, I guess. What about observers? If you look at any book on quantum theory, you'll see a lot of talk about observers, and if you take a book on classical theory, usually you won't find observer in the index. Maybe in a book on general relativity, but even there they're not really important. The point is that an observer doesn't add anything to the theory. There is a way things are, physical quantities have their values, the time evolution goes on, and that's all fine. And an observer does nothing more than reading off these values, for example. He doesn't add anything conceptually, structurally. And this is in great contrast to quantum theory, where observers are crucial. You don't get anywhere without observers, you just need them conceptually. We'll see why this is. And moreover, the observers in quantum physics are classical. They are not quantum systems. So you have these two levels. You have the quantum system itself, but you have another level of classical observers, and you can't do without them. And that's actually part of the problem. And this relates to the fact that the interpretation of classical physics is realist, while that of quantum theory mostly is instrumentalist. It's almost forced upon you. There's a logical structure behind these things. There's Boolean logic in classical physics. That's just really familiar logic. There is something called quantum logic, but it's very doubtful whether this is a useful logical system. So I put a question mark there. Of course, I could debate ontology endlessly, and I was just bold by saying it's unproblematic in classical physics. There would surely be philosophers and scientists disagreeing with that, but basically it's not problematic, while in quantum theory it is. As this Fuchs said, when do we finally stop burdening the taxpayer by asking for conferences on foundations of quantum theory? And this has been going on for 80 years, and we still haven't settled on a good ontological understanding of quantum theory. So, of course, it didn't stop in 1928. Quantum theory was still applied much more broadly, and new phenomena were discovered. There are things like spin, which is a purely quantum theoretical physical quantity. You didn't see this classically. It's very, very important. For example, leads to a distinction between particles and fermions, which have half-integer spin, and bosons, which have integer spin. They play very different roles in our physical theories. Antimatter was predicted and found, and so on. So this was a successful theory, which soon was applied much beyond its original scope. And of course, the question came up: if I really want light and matter interacting, I should combine quantum theory and electrodynamics. And this was actually a very hard problem, and it took people to roughly 1949. So it's Feynman, Maga and Schwinger, they got the Nobel Prize for that. I mean, of course, there was Second World War in between, people did other stuff, but still it was 20 years till this was figured out. And quantum electrodynamics is the first quantum field theory, and this describes the interaction of light and matter by the electromagnetic force. And this is also what is called the gauge theory, and there was another deep principle in physics discovered after 1930, probably is the gauge principle. So deep concepts come rarely, so every 50 years maybe. I would argue the last really big one may be gauge principle. So we won't go there much, but it's elaborate, and there's a lot of stuff going on. There are two other fundamental forces, so-called weak and strong force. They're both acting on the level and the distance of atomic nuclei, so we don't see them in everyday physics, but on the one hand you may wonder, why do these charged particles, the protons, which are positive charge, why do they even hold together? Because they should repel each other. They do actually, but there's another stronger force which keeps them together, and this is strong force actually. And the weak force plays a role in things like radioactive decay. They were also described in the 60s and 70s by quantum field theories. It was much harder, and then finally people arrived at what's called the standard model. This was in the 70s. This describes these three forces: electromagnetic force, weak and strong one, in one combined theory. And this is an extremely good theory. We have no experimental results which would contradict the standard model, which would tell us, okay, this is wrong, and here we have to think harder. This is actually part of the difficulty of going beyond this, is that we have no strong hints where to look.
Can I ask
Sure.
you a question? Well, from what I know, one of this, the results worked out in the standard model is some I don't remember how it's called, some constant related to electron.
Yes.
And what puzzles me is that they usually give you with 22 digits
yes.
precision,
Yeah.
and then so the question is, what happens in 23rd digit or whatever? Whether the discrepancy is due to non-precise measurements, or it is proved to be some discrepancy that is in the model.
Okay, so yes. Well, first of all, I think what you're referring to is the magnetic moment of the electron, which actually can be calculated from QED. And QED predicts this, I think realistically, 12 or 13 digits. And of course there are precision measurements which go to the same level. Otherwise we wouldn't say it's confirmed. Otherwise it's just a calculation. And you couldn't claim it predicts this to this degree. But when people say it predicts it with this precision, then it means we can actually measure it with this precision and compare prediction from theory with it. So you can, don't ask me how. This is experimental physicists are very, very good at doing these things, and it's not easy to understand how to measure this thing, but I can look this up if you like. And also how to calculate in this theory is very well understood. I mean, it's over 60 years old now. And, as you probably know, the calculations actually are perturbative calculations. So you pretend that the system is, well, first of all, it's almost like non-interacting, so just the particle flies along and there's nothing acting upon it. And then there's a small correction to this coming from the interaction, and then there are small corrections on that. And the higher you go, the harder the calculation becomes. But in QED, well, again, I could be wrong because I've done calculations like that, but I think people can go up to level 7 or 8 in this, they call this loops, because there are particular terms which are represented in certain Feynman diagrams by loops. They are contributing to these corrections mostly. So you can go awfully high, while in other theories, level 7 or 8, it's very involved, but you can do this. And of course, computer algebra also helps partly. In other theories, you're very glad if you can do loop 2 or loop 3, loop order 3. So this basically comes down to the fact that the gauge field in QED is, the gauge group is U1, which is an abelian group, which makes your life easier. Well, for the weak force you need SU2 tune for the strong force, you need SU3, which of course are non-abelian, and your life gets much harder. And, there is, well, it's an enormous industry of people who have worked on this, but if people say it is precise to this or that degree, then of course there's an experiment confirming this. It's not just the calculation.
Yeah, so for me it is very important, question is whether we still hope that if all these methods of perturbation theory, I mean, if the method of calculations we exacted, then we'll see further digits coming out correct, or it is something that we can, it is simply we ignore it. In terms of physics, it is unimportant that it is some discrepancy in 20-second orders.
In terms of physics, we are pretty sure that the standard model is not fundamental. The common view nowadays is the so-called effective field theory, so there should be something underlying, which probably has to do with quantum gravity in some sense. This excludes gravity, and this is of course what we'll talk about in a minute. In this sense, there is maybe a certain limit beyond which it may become a bit futile to calculate even more digits, because then corrections from other theories may come in. They may be very weak, but 22nd digit you may actually see it. And this is, it's still, another topic is that these perturbation series are not actually convergent. They are asymptotically convergent. So basically you have to know when to stop, because if you sum too many higher orders, you actually get a worse result again. And I must admit I don't know much about these actual calculations, and mathematics is, well, the technique is pretty involved, in the mathematics of asymptotic series, of course, is also not easy to see. So currently we're not at the level people say, okay, we have to stop. You still get better results by calculating higher orders. There is, I wouldn't know a physical phenomenon which is actually dependent on the 22nd digit. Okay. Now if you look at how progress in physics historically has been made, this has very often been by a process of unification. For example, actually you can see Newton's theory in this slide, because Newton realized that mechanics going on in the sky is the same as the mechanics going on down here on Earth, which was for the time an enormous step. And he said the same laws apply, and in this sense his theory was unification. Maxwell, of course, unified electric and magnetic phenomena into electrodynamics. You can see special relativity, if you like, as a unification of mechanics with symmetry concepts which come from electrodynamics, because electrodynamics already told you something about the symmetry group of space-time, at least implicitly, which was different from the Newtonian space-time that we had used in mechanics so far. Of course, a theory like quantum electrodynamics is a unification. It takes quantum theory and electrodynamics, and there are further examples. So this is just empirically something you could try to achieve, the unification of theories to get something deeper. And it always turned out that the older theories were never completely invalidated or replaced by the new ones. They were just incorporated and subsumed, often in an unexpected and very subtle way. And it's by no means true that once we had special relativity, threw away the classical mechanics, and once we had general relativity, we threw away special relativity. It's just the case that the older theories, they have their range of application, and if you want to calculate, I don't know, if you kick a ball, how it moves, you will not use general relativity to do that in general. Yeah. Use mechanics, classical mechanics, and that's fine. It applies very well. And of course, it's contained in a suitable sense in special relativity and also in general relativity. Okay. Oh, there's one big thing missing, of course. We have 4 fundamental forces, as we believe today. So 3 of them are electromagnetic, weak and strong force, but we also have gravitation. And we have a very good theory of gravitation, which is general relativity. So why not unify quantum theory of gravity? So why not do quantum gravity? And very clearly, since this would actually incorporate everything into one theory, quantum gravity, or even more obviously a theory of everything, TOE, which obviously has to be in uppercase letters. Describing all 4 forces would be the pinnacle of physics. So people have tried that, believe me. They've tried very hard for a very long time. In principle, they could have asked this question in 1928. As far as I'm aware, they didn't. But at least from the 1960s on, there was an enormous amount of activity, and there still is, of getting at a theory of quantum gravity, or maybe a theory of everything. It's very little progress. Of course, we understand things better, but we mostly understand what doesn't work. String theory largely was an attempt at a theory of everything, but has failed to deliver on this. So for a physicist working on foundations, finding quantum gravity is the most important problem. This is actually the big fish. Yeah. This is what, this is really where the big boys play. But it's very hard, and nobody actually makes progress. So I'm saying this tongue-in-cheek because I'm surely nowhere near this, and very good people have tried. So, what did they do? What did they try? Well, there are basically 2 main classes of approaches. There are further smaller approaches, but 2 main approaches. The first kind is called canonical. And what you do there, you take your 4-dimensional space-time and split it up into space and time. And this 3+1 split is not canonical. There are lots of ways of taking space-time and splitting up into space and time. So you should take care at the end of the day that this particular split that you took does not actually influence your physical predictions. If you do so, then the idea is to implement some quantum version of the spatial aspects of gravity on this 3-slice, and then to move this 3-slice through time. And one of the hardest problems that you come upon there is that this time evolution, if you like to call it that, it's described by an equation of this form, and that's very odd. The reason is equations in this canonical approach are constraint equations, and they take this form. It seems that, well, your Hamiltonian, which describes the time evolution, should annihilate your quantum state. This is very odd. It's very hard interpretationally to see what to do about this. This is the problem of time, well, the associated interpretation problems. The other big class of approaches are covariant approaches, which keep the full space-time and try to formulate this theory directly such that it respects the full diffeomorphism group, which is the symmetry group of general relativity. People from particle physics tend to like this more, people from general relativity tend to like this more with decades. Anyway, so particle physics people would usually use perturbative and path integral techniques, which are highly problematic technically and conceptually in this situation, because gravitation is so different from other field theories which just take place on the space-time background with a fixed metric, but now the space-time metric itself becomes dynamic. Of course, there are lots of other approaches, but it's fair to say that there's no predictive theory and there's no convincing conceptual framework. So this is really hard. So why is it so hard? First of all, we have no experimental data. That we could actually say, this is from quantum gravity, this is data I would have to explain. And why is that? Well, every physical theory has a natural energy and length scale, so where the phenomena of this theory are important, and is expected to be for quantum gravity. Well, nobody knows the theory, so it's very hard to say, but there are some dimensional arguments which are actually very simple-minded, but it's not stupid to say this. It's expected to be that for quantum gravity, the energy scale is the so-called Planck energy, which is, well, this more or less impressive number, and the length scale is the Planck length, which is, well, this may be a bit more familiar. You see that this is really awfully small. Both of these scales, I hope I'm not entirely wrong here, but roughly 15 orders of magnitude away from what we can test experimentally. So there's no hope that any of us will see an experiment in our lifetimes actually testing these scales. Very first moments of the universe after the Big Bang, at the interior of black holes, are physical situations where you would expect quantum gravity to be important. Of course, these dimensional arguments are not entirely conclusive. You may hope, and that's of course the hope, that a theory of quantum gravity, or maybe a theory of everything, manifests itself not just on these scales, but trickles down to other scales, and it can see something in our lifetimes, because after that it's not that interesting. But equally important is the fact that there's a conceptual clash between quantum theory and general relativity, which after all is a classical theory. And this happens on many levels, but I just want to say very vaguely here that many of the conceptual problems already exist in non-relativistic quantum theory. This is actually what we mostly look at, because I can't possibly start a quantum gravity course here. And I couldn't. Some of these problems that you have in non-relativistic quantum theory become harder if you apply them to gravity when space-time concepts come in. And then there are some problems which are actually specific to gravity and physical situations where space-time itself becomes a dynamical object. As I said, we'll mostly consider non-relativistic quantum theory with an eye towards conceptual issues, and if you want to read a bit more about quantum gravity, the way to this in quantum cosmology, have a look at these. These are excellent objects. You might say, oh, they're pretty old, so why should I look at this old stuff? Well, there's not much progress since then. And Chris maybe is actually the best author writing on this stuff, and it's really a pleasure reading this, and you get a very good idea of what the conceptual questions are. This book by Lee Swallow, I must admit I haven't read this one, but it's a popular book, and of course I can point you to technical articles if you like, but if you want to get an idea what is going on, what people are thinking about, and what the problems are, I think these are very good references. Okay, so now we've taken a big tour through all of physics basically, and now I'm in a position to say what the Topos project actually is about, because that's where the motivation comes from. What we try to do is to identify some key conceptual problems in quantum theory and quantum gravity, and then to provide a framework in which, well, first of all, we can formulate existing physical theories, which are good theories that we know, like classical theory and quantum theory. Of course, in a way, addressing these conceptual problems, and we'll see that this actually means that we have to change quantum theory, because as I said, there are conceptual problems in standard quantum theory already, so we would not be happy just to keep this, and it's just, you can say it's kind of pragmatical, because many people have tried to keep quantum theory and do quantum gravity, and they've all failed, so maybe for this reason it's just a good idea to do something else. And of course we want the framework to be flexible enough to accommodate theories beyond quantum theory, so we want to have something which is not specific to what we already have, but hopefully gives us some ideas how to go beyond this. Of course there will be, in the concrete realization of this stuff, there will be technical results from different fields actually that come together. but different from the usual approaches to quantum gravity. It's not accepting quantum theory as it is, because basically all of these approaches take quantum theory as it is and then mostly try to adapt gravity to it. And this just has failed so often that it may be a good idea to actually try to do something about quantum theory first. And of course, if we're lucky, and I think this actually is happening, we learn something about foundations of quantum theory itself. So if we're not interested in quantum gravity at all, we may still be interested in foundations of quantum theory. But yeah, when I say framework, I mean this seriously. This is not about a specific theory. This is not about saying, the hydrogen atom now looks like this. I mean, eventually we should be able to do this, but it's more about giving a mathematical framework, saying in general what kind of mathematical ingredients, what kind of mathematical shape should the theory of physics have. And then of course you have to show that things we know fit in. And as I said, we actually have to find a new mathematical formulation of quantum theory, and then some people say we're crazy because this hasn't been done in 80 years. We are still using Hilbert space formalism, which was done by Fanon, and it was really in place in 1930. So quantum theory is Hilbert space theory. And of course we have to connect with that. We don't do the same thing. Well, we make some progress, there are lots of open questions, but so far interesting things come up, interesting mathematical structures come up, so there's some hope that we can do something. So what are the key problems? We'll take a break in 2 minutes, well maybe not 2 minutes, but in a few minutes. We mostly concentrate on these two. The first thing is the mathematical formalism. Quantum theory is usually interpreted in an instrumentalist manner. This relates to all these things that I talked about in this table comparing classical and quantum theory. I say, okay, there are odd things in quantum theory. This basically all relates to this. And the second thing, so this comes from, well, foundations of quantum theory itself. This is more motivated from quantum gravity. I mean, the fact that all physical structures are based on the idea of a continuum, and their mathematical description uses numbers in a fundamental way. So, say something about both of these problems. Why are they problems? When I say instrumentalism, this means that you have an interpretation of the mathematical formalism, which involves measurements, observers, and all these notions. And for example, when Bob and Sampson talk about preparing a system and then measuring, this is also this is called operational. This is also instrumentalist in this sense. This is a well-known problem of quantum theory, but why is it a problem? I mean, instrumentalism does not weaken the predictive power of quantum theory. It does not keep us from enlarging the domain of application, and as we've done in the past, enormously beyond what was initially envisaged. And moreover, isn't that what we do in physics? We prepare a system, well, it evolves, and then we perform a measurement. So that's what it means to do physics. So why is there a problem? To be fair, many people don't see a problem. So why do we think there's a problem? The point is that quantum theory does not describe a quantum system. It only gives us a recipe how to calculate the outcomes of experiments. And usually this comes with a statistical prediction. And there is little to nothing that we can say about the quantum system in itself when I do not perform a measurement. And then you have this level of measuring devices and observers, and this is not described by quantum theory because these are classical. This means that seemingly more fundamental theory, which should be quantum theory, completely depends on the less fundamental theory, which is classical. And this is a very odd situation. And maybe as a slogan, there's no picture of reality arising from quantum theory itself. You don't know how a quantum system is in itself. You can only say something very successfully what you will see if you perform measurements. Another thing is that nobody knows at a conceptual level what a measurement is. And you're pretty sure if you do a measurement in a laboratory that you're actually performing a measurement, but which physical processes are measurements? Nobody really knows. I said some of the problems get worse if you want to apply them in situations which have gravity or space-time aspects, and instrumentalism is one of these problems. And here are some things that actually get worse if you apply them in quantum gravity. So if we want to treat space and time as quantum objects, whatever this will mean in detail, because we don't know, what could a measurement of space or of time mean? Or asked differently, where and when would such a measurement take place? The very notion of measurement seems to require a space-time background, which is not there in this kind of theory. In quantum cosmology, at least, we will have to treat the whole universe as a quantum system. Where's the observer? There's no one sitting outside the universe performing measurements on this system. Of course, we're by no means the first to say that. This is all well-known stuff. And usually the conclusion is we need to overcome or circumvent instrumentalism. So we need a more realist formulation of quantum theory. And this has been tried. Of course this has been tried. A lot. And the results mostly were strong no-go theorems, which actually tell you, okay, any naive attempt will not do. Many aspects of quantum theory actually is very different from classical physics, and things like Bell, specular, non-cloning, naiveity, they're all telling you, okay, you won't get away with any naive realist notion. Okay. So what's the problem with the continuum? So this is more motivated from quantum gravity considerations directly. You wouldn't worry about this in quantum theory usually. It is commonly expected, this is one of the few things that people agree upon in all these approaches to quantum gravity, that at very small scales and very high energies, these Planck scales again, the continuum picture of space-time will break down. So nobody really knows what happens, but people don't expect that the manifold will still describe space-time at these scales. But manifolds, of course, are objects which we describe. They look locally like an Rn. This is where your continuum picture goes into the description very directly. A bit less directly is if you think about how do you actually measure something. So if you measure distance, well, you take a rod, bring it there, and well, you read off the distance. But this also presupposes something about the nature of space-time, namely that you can move your rod there continuously, or you read off where a pointer stands on a scale. But again, there's an underlying continuum where these physical objects, your rods and your pointers move. So if you take it seriously that your manifold picture may disappear, you may actually be less convinced that physical quantities necessarily need to have real values in the usual sense, and values along a continuum. The third thing which I didn't put on the slide, but which also relates to this instrumentalism aspect, is talk a lot about probabilities in quantum theory, and of course they are also taken from continuum between 0 and 1, and the discussion about the nature of probability, of course, is even older than discussion about quantum theory, but also there, why should we be able to compare any two of them? Why shouldn't we just have a partially ordered set instead of a totally ordered one? At least one may speculate in this direction. Now, this is very easy to say because, well, okay, it sounds somewhat plausible, but it's very, very radical if you take this seriously, because all our structures that we have mathematically in the theories that we have today, manifolds, Hilbert spaces, operators, path integrals, strings, loops, and so on, they all are based on continuum ideas. So if you take this seriously, we'll actually have to depart very radically from what we have today, which we may have to do in quantum gravity. But there are other reasons which are more down to earth, and even if you don't buy this, this is still true. Since we have non-commutativity of physical quantities like position and momentum, the concept of the state space of a quantum system becomes problematic. There is no state space of a quantum system as we have for a classical system. So ideally we would like a framework for the formulation of physical theories that does not fundamentally depend on real numbers. And we've only made a little progress in that direction, to say this clearly. Okay, I think now's a good time for a break, and this part is actually very short, so I just want to say a few things about quantum theory, but this will just lead into what I was going to say. So this would finish the introduction and the conceptual remarks. Of course, I'll have some conceptual remarks in between, but everything we will see from now on is more technical and is an attempt to provide such a framework for the formulation of physical theories, and mostly actually to show that quantum theory fits in. It is very clear actually, and we'll see this more clearly, that classical physics fits in. There's nothing much to be said about this. But the realist formulation of quantum theory, or at least some steps towards this is beyond. So I say let's take a break at this point.
Yeah.
Okay, thanks. I just want to say some very basic things which all of you know. It's, well, more or less getting notation in place and giving us a starting point for next time. We'll talk about things which may be less familiar. So, of course, this will not be a complete introduction to quantum theory, but we'll introduce basic structures and some function analytic concepts that we'll need later on in the Topos approach. If you want to read something about quantum theory from a conceptual perspective, of course also with technical details, then these are two very good references. This has a slightly pompous title, but it's a very, very good book. And obviously it covers much more than quantum theory, but you can learn a lot about history, but also about things we will be using, and of course much more. And this is a very good book. So I'm quoting Chris a lot, but it's actually because he writes very well. It's a good book and it's cheap. Okay, you've seen this, but anyway, here goes. So pre-Hilbert space, E, is a vector space over some field K, which has an inner product, or scalar product, from E times E to K, such that these things hold. So for all lambda and mu from the field and all three elements x, y, z from your vector space, you have that this inner product behaves in this way. I think I don't have to read the formula. You see that it's linear in the second argument. Secondly, you have for all x and y in your pre-Hilbert space that, well, the product of x and y is the conjugate of y and x. And finally, you have that for all x in E, the inner product of x with itself is larger or equal to 0. It's only 0 if x itself is 0. Note that inner products are linear in the second argument. This is a convention. This is the usual thing for physicists. Mathematicians often have linearity in the first component, but those mathematicians working in physics a bit, they usually adapt to the physicists' convention. So we'll have the physicist convention here, and of course from this rule you see it's antilinear in the first argument. And now Hilbert space is a pre-Hilbert space that is complete with respect to this norm. So just taking the square root of the scalar product of x with itself gives you a norm, and if completeness in this norm, we have a Hilbert space. And from now on, as always in quantum theory, we assume that we have complex Hilbert spaces, which just means our field is the complex numbers.
This may be very stupid, but does every field have to be ordered? Because your third condition of the product assumes that.
No, this is. I think it's a good question.
Well, actually, if you agree to play with complex conjugation,
Yeah.
then you already agree to have reals in it. That's
Yes, I should actually have said it's either R or C at this point. I should have said this. I'll edit the slides before I send them out.
yeah, but this is definitely the point that we have been struggling with, because from model theory point of view,
Yeah.
having abstract, say, algebraically closed field,
Yeah.
or the field where you can identify reals,
Yeah.
it makes a big difference. And
Yes.
in this approach, you have to assume that reals are in your field, as long as you are
Yes.
going to assume this complex conjugation plays a role.
Yes. It's a good point. I should have. Well, I shouldn't have pretended to talk about general fields at this point. When we speak of bases, well, these are vector spaces, so they have bases. And when we speak of bases, we always implicitly mean an orthonormal basis. And this means the following. So you have spaces EI, and I runs from 1 to the dimension of the Hilbert space, which can be infinite. Then for all I and j from this index that you have, then the scalar product is delta I. It should be common. It is a common, I think. It's a bit hard to read. Delta I, comma j. You can drop this comma. It's delta I j. This is the usual symbol called the Kronecker delta. It's just 1 if these two coincide, and it's 0 if they don't. So any two basis vectors which are different are orthogonal to each other, and you'll see in a second that each of them has length 1. Well, we actually see this already, because if you have EI here, you get the square of the norm, but this equals 1, then of course the norm is 1. Okay, so what are examples? Cn is a Hilbert space, and the inner product is given this way. Take two x, y, and you write them on a certain given basis, EI this way, and then the scalar product is this. It's clearly linear in the second, anti-linear in the first one. Mathematician immediately says, why, what about basis? Does it depend? Well, it does not. We'll see this later on explicitly, so it can pick any orthonormal basis, and this definition doesn't depend on this. Another example is basically taking n to infinity, as my theoretical physics professor said. So we can take C omega, which is an infinite dimensional Hilbert space, and the inner product just looks like this. This is what's called a separable Hilbert space, which means it has a countable basis. And usually physicists look at these guys, so we'll also assume that our infinite dimensional Hilbert spaces are separable, have a countable basis. Of course, there are lots of more examples that show up, so these are maybe not the ones you will usually find. These are the ones you find in quantum information theory, for example. I should also say that in my whole list of physical theories, quantum information theory didn't show up. This is because I will say a bit more on the way, but also because I think it doesn't make much sense to talk about quantum information theory before you don't know quantum theory a bit. I shouldn't say this next week when I'm starting to lecture on this stuff and people don't know quantum theory, but here I can say it. And, so we'll first do a bit of quantum theory and then specialize to quantum information theory. In some sense, of course, these are the only Hilbert spaces, mainly in the sense that, well, a vector space is completely determined by its dimension. Then you have to think about how the inner products translate to each other if you have some other Hilbert space. But let's stay with this simple example for now. We may see more complicated examples later on.
Sorry,
Yeah.
I have a question about. I have been confused about. Well, I spent a lot of time trying to understand the notation that. So your notation are different from this bracket notation.
Yes, the Dirac notation is, well, it's slightly abstracted from the inner product, of course. It's not very far from this. I avoid it here because there are subtleties in infinite dimensions which you can all sweep
so
under the rug.
They use the Dirac delta rather than Kronecker delta in the definition.
This is no, not for the basis. This is if you have situation. Okay, Yes, this is because they want to talk about eigenstates of unbounded operators like position. Then you have expression like delta x minus y, but delta is now the Dirac delta. The point is that you're actually moving out of Hilbert space at this point, as you know, so you have to get to rigged Hilbert spaces, and I'll avoid this stuff. So our operators will mostly be bounded, and I'll just say, okay, unbounded operators can be affiliated to our operator algebras later on. So we'll avoid this. There are lots of issues there, and okay. So linear operators, also nothing mysterious. So K again is R or C. Linear operator between K vector spaces E and F is a mapping from E to F. Well, that's linear. It just means you have this for all. Oh, I have. This should of course not be H. This should be E. For all X and Y and E, and for all scalars like mu. This linear behavior. We mostly consider linear operators on a given Hilbert space, so A goes from H to H. And that's actually almost the last thing I want to say. A linear operator A. By the way, I'm a physicist, so operators get a hat. This is just the usual notation in physics, which has a hat as an operator. Linear operator between normed spaces, and we know our Hilbert spaces are normed in particular, is called bounded if the following is true. If the supremum of all these numbers A applied to X, where X is taken from the unit all, if this is a finite number, then the operator is called bounded, and this number is denoted this way, it's called the norm of the operator. And the operator is continuous if it's a continuous mapping the norm topology on. Again, here, sorry, I first wrote it all for Hilbert space and I thought I should do it more generally, so anyway, I'll fix this, because it means now the norm topologies in these two spaces here. We will actually, I think, exclusively look at operators from one Hilbert space to itself, so this level of generality should be here for once, but not beyond this. Note that this notion of boundedness is different from the notion of boundedness as a function, because if you have such a linear operator as a function, it will not be bounded. You can get operators of arbitrary norm, because you just can increase the norm of your argument, unless your linear operator, of course, just gives you constant value. So boundedness of operators is something different from being bounded as a function. And you see that in order to avoid this, of course, we take these vectors that we put in here as arguments just from the unit group. I was just saying, if you take them from everywhere in your Hilbert space or in the norm space, and of course there's no guarantee that this number will stay finite. It will always be infinite unless your operator just gives you a constant output. Okay. Clearly, in finite dimensional Hilbert spaces, if you think about it for a second, you'll see that all linear operators are bounded and continuous. So that's nice and easy. But things get more complicated once you go to infinite dimensions. There you can have unbounded operators, and then you wonder how do these notions of bounded and continuous relate to each other as a theorem. This actually needs a proof, which I will not give because it would take us too much time. But we can prove that a linear operator between normed spaces is continuous if and only if it is bounded. So these notions they actually coincide, and this of course indicates for the first time that in infinite dimensions many things happen that you just don't see at all in finite dimensions. So the infinite dimension theory is much richer than the finite dimension theory. And we need unbounded operators in physics. Typically, if you describe position momentum, you get unbounded operators. Well, the particle can be anywhere in space. And we'll talk about maybe these operators a bit more in detail, but definitely we'll talk about things like the spectrum of an operator and algebras formed by operators and representations of these algebras next time. So this is all very basic, but it gives us a starting point for doing it. analysis just to the level that we actually need in the approach. And after this, I'll actually talk about categories and talk about it. Okay, are there questions? Doesn't seem to be the case.